Welcome back to Discrete Math. Today we're going to do some practice problems on mathematical induction. You're going to need to know the divisibility lecture. I know it's ahead in the course, but for these questions I want to do something more than just set questions or logic questions or sum questions. So you need to know divisibility for these. So that being said, let's begin. We want to prove that n cubed plus 2n is divisible by 3, where n is a positive integer. So again, what are the two steps in mathematical induction? First is the base case, and we're starting with n is equal to 1. So let's plug 1 into n cubed plus 2n. Well, this is going to be 1 cubed plus 2 times 1, which is 1 plus 2, and that's equal to 3. Therefore, we know that 3 is divisible by 3, so we're good. Next is going to be the induction step. So our hypothesis is we're going to assume n equals k is true. Okay, so what does this mean? This means that 3 is going to divide k cubed plus 2 to the k. So by definition, this means that 3 times m is going to equal k cubed plus 2 to the k for some m in the set of integers. So we know this is true by definition, and of course the pen is giving me troubles. There we go. Okay, so now we want to show that n is equal to k plus 1 is true. So let's substitute k plus 1 for n. So we're going to get k plus 1 cubed plus 2 times k plus 1. Let's expand this. So k plus 1 cubed is going to be k cubed plus 3k squared plus 3k plus 1. We know that from the binomial theorem. And 2 times k plus 1 is going to be plus 2k plus 2. Let's group our like terms and see if it's divisible by 3. So you have k cubed plus 3k squared plus 5k plus 3. This isn't good. It doesn't look like it's divisible. But what do we know? We made the assumption that 3 times some number is equal to k cubed plus 2k. So let's pull out a k cubed plus 2a, or plus 2k. So k cubed plus 2k. And then we have our remaining bits. So this will be 3k cubed plus, well, we took 2k from 5k, so we're left with 3k. And then we're left with 3. Good news. So now our k cubed plus 2k, we said that was equal to 3 times m. And with our remaining, we can factor out a 3. It's going to be 3 times k squared plus k plus 1. And then we can factor out a 3 from our 3m as well. This is going to be 3 times m plus k squared plus k plus 1. So this, we know, is an integer. And we also know that our k plus 1 cubed plus 2k, or 2 times k plus 1, is equal to 3 times an integer. Therefore, we can say that 3 divides k plus 1 cubed plus 2 times k plus 1, and therefore we know, because the base case is true and our inductive hypothesis is true, that 3 is going to divide n cubed plus 2n for all of our integers. So that's the first proof. The second proof, we're going to prove that 2 to the n is going to be less than n factorial for all n greater than 3. So this is the same thing as saying n greater or equal to 4. Okay, so 2 steps. One is the base case, the other one is the inductive hypothesis. So for the base case, we're going to have n is equal to 4. So let's plug in n equals 4. So 2 to the 4, this is equal to 16. And we're saying this is going to be less than or equal to n factorial. So that's going to be 4 factorial, which is equal to 24. So we're good here. This may be a little bit confusing because I'm writing equals and less than. So this holds for everything. So I'm saying 2 to the 4 is equal to 16. And that's going to be less than 4 factorial, which is equal to 24. It's going to get confusing for the next part. So now, for the inductive hypothesis, we say that n equals k is true. So what this means is that 2 to the k is less than k factorial. We're establishing that. And now we're going to show that n equals k plus 1 is true. So let's start with substituting in n for k plus 1. So we're left with 2 to the k plus 1. And can we write that differently? Well, yes, we can. We can write that as 2 to the k times 2. So what do we know here? 2 to the k is less than k factorial, and we know that by assumption. So that is our assumption here. Now what about 2? Well, 2 is also going to be less than k plus 1. Now why is 2 less than k plus 1? Well, so we have n is equal to k plus 1. But what is the minimum value for n? We're saying n greater than 4. So this k plus 1 is not going to be less than 4. And 2 is definitely less than 4. So our 2 is going to be less than k plus 1, no matter what our k plus 1 is. And what is k factorial times k plus 1? That's the same thing as k plus 1 factorial. So we've proven here that this 2k plus 1, I'll do this in a different color, that our 2 to the k plus 1 is less than k plus 1 factorial. So we've proven our inductive step. So now because the base case and the inductive hypothesis is true, we know that 2 to the n is less than n factorial for n greater than 4, greater or equal to 4, where n is in the positive integers. So that was mathematical induction. If you have any questions, please leave them in the comments below. If you have any other induction questions you want done, please leave those as well, because these questions are really good, because induction is a very, very important thing in math. So hope you enjoyed the video.